Great. Thank you very much for inviting me down here. It is really, really exciting to be in Sao Paulo. It's a very vibrant, exciting, and welcoming city, so thank you. I'm here to talk to you about NLP architectures, but before we get too deep into it, just to give you some context on who I am. My name is Michele Casbon, and I'm an engineer for the Google Cloud Platform. And prior to that, I was working in a few startups based in San Francisco, building machine learning applications in the cloud. Started with AWS and then moved on to Google Cloud Platform. And there's been a focus on multilingual natural language processing applications. But prior to that, I spent over a decade as a data engineer. So that's given me some good context, and I'll take you through some of the things I learned in my career, kind of the good, the bad, and the ugly in the NLP world. To give you a rough idea of what I'll go over today, we're going to talk about how NLP architectures have evolved over time, what they looked like in the beginning up until today. We'll talk about the components, what makes up an NLP application, and I'll take you through some lessons learned. We'll go over just a few of the guiding principles, some sort of common denominators that I've seen in successful applications. And I'll show you a few examples from a few different implementations that are running in production, and then we'll talk just pretty briefly about what the future looks like. So just to start off, before you start building an NLP application, my friend David deserves the credit for this slide. I saw him speak at the last QCon in San Francisco. You should always ask yourself, is the problem that I'm trying to solve, is this clearly defined? Because if not, you really shouldn't be anywhere near machine learning. So define your problem first and make sure that that's super clear. And once you have that problem, then you want to make sure that it can't be solved in any kind of simple, deterministic way. Because if there's any other way to solve your problem, machine learning should kind of be your last resort. Go do that. But if there isn't any other way and you're convinced that you absolutely have to employ machine learning, then go for it, get started. But it's not always the answer. Despite what you may have read in thousands of blog posts, it is not a cure-all. And counting things is still really hard, and I've seen that a lot of my coworkers, some of the problems that they've been working on, they can really just be solved by counting. So do that first. Don't just start out with machine learning. Okay, so what have architectures looked like in the past? So they started off as these sort of handcrafted artisan systems. They were hard-coded and rule-based. I want you to think sort of spell checkers attached to typewriters or grammar checkers. These were all very meticulously composed, and as a result, they were really hard to update. So when things changed, language is a very dynamic thing. It never stays the same, and those systems were very hard to update. They got stale pretty quickly. So we moved pretty quickly into these kind of Frankenstein systems where we cobbled together pieces with tools from other domains. And this worked mostly for, like, logging and monitoring was pretty standard, but it was a little bit more unwieldy when it came to things like data versioning and model packaging. It didn't work out so well. And this really kind of represents the sort of assembly language phase of machine learning, where before we had higher level languages like C and C++, people were programming, they were sort of copying values between registers, and they were operating at a really low level. And that's what this era represents. It's getting into the guts of the math and multiplying vectors together, and it's really kind of deep down. And so the next era, this is where we are today. We're just at the very beginning of this era, but we're working on building more purpose-built tools that are specific to machine learning. They can handle a variety of resource demands. It's not one size fits all, and they can handle them independently. They're scalable, they're flexible, they're resilient, and reproducible. And most importantly, they're maintainable. That means that They don't get stale, they can be easily updated, and they operate more on the principle of composability. So instead of being deep down into the math, there's a lot more, more like Lego pieces and putting things together at a higher level. And that's sort of, we're just at the beginning of that era today. And in the future, where we see ourselves headed after that is where it's almost trivial to build a classifier, where the quality of our models are based solely on the training data that we're sending into it instead of all these lower level additions, subtractions, and matrix multiplications. So let's go over a few examples. These are some places where you might see NLP applications. The first is just your sort of canonical web app. This is most common in especially startups. You'll see this kind of everywhere. And this is your sort of standard microservice architecture where you have lots of different pieces of business logic, and all of that is all that comes together in a layer that talks to the front end. Your user accesses via the front end, and one of those microservices might be specific to machine learning, to NLP. And that'll talk to a back end, transactional, maybe analytical, and you'll have a place to store some of your NLP models. This is a really common model that I see. You might also find NLP in a data warehouse system, where you have lots of different applications, lots of disparate data sources that all come together in an ETL layer and is put together in an analytic data store in some kind of data warehouse, and then perhaps enriched with some sort of NLP and used for analytics of some type. That's pretty common. Or you might just see it as part of a generic data pipeline where you have some type of source data and you're doing some sort of transformation. Maybe you're formatting some of it, you're doing a lookup, you're connecting it with another data set, and then you're enriching it with some type of NLP and putting it into some sort of transactional store that's used further on down the line. What's inside those NLP microservices? Well, it could be just one, but usually I see it broken down into different pieces because each of these steps has a very different resource footprint. They have very different resource demands. Some of them require a lot of CPU, a lot of RAM. The training data preparation phase usually isn't super resource intensive, but this is where you ingest your data, you transform it in some way, you might validate it, perform some type of analysis on it. But training is the real resource heavy. This is the heavy hitter of all of the NLP components. And this is where you're going to want to use as many resources as you can, especially if you have a very large volume of training data. You're going to want to segment that in different ways because you can see different model performance depending on how you segment it. So segment the data, then featureize it, and then actually build your model out of it. And another piece of the NLP puzzle is the serving layer. Once you've trained your model and you've built it, you're going to want to do something with it and serve up some predictions. This is where you wrap your model in a REST server and you make it available for other parts of your application to call it and access those predictions. So first, you'll just retrieve the model, you'll perform the same featureization steps, get a prediction from your model, and then return it to the caller. And another common component that I see is the evaluation phase. Tenfold cross-validation is pretty standard, and that's where you validate that the predictions you're serving make sense, that your models are accurate, and that you're not just sort of spewing out a bunch of junk. And that looks a lot like the training phase, except that you're cutting up your training data into different pieces. You're doing the same featureization steps and calling predictions, but then you're also evaluating it to make sure that it's accurate, that it looks like you expect. What we'll focus on for the rest of this talk is mostly the web application. So this sort of canonical, very common, larger architecture that NLP is kind of one piece of, an important piece, but just one piece of. So let's look at some of those components more in detail. I've noticed this perception, and maybe just because machine learning is not well understood right now, or maybe it's the hardest piece, I don't know, but people tend to think that it's just this humongous part of any application. And in reality, that looks a bit different. That training component really is a very small piece, and you may spend an exorbitant amount of time on it, so it may feel pretty large, but it's actually really small. And in general, the components of one of these systems, they fall into 5 major categories. The first is data, obviously. You have to be able to ingest the data, do some exploration with it, clean it, transform it, get it into a state that you can do something with it. Validate it to make sure that as you're getting in live data, it's still accurate, it's still valid, and you'll want to understand the histogram, what that data looks like, how it's changing over time, so there's an analysis piece. And then, of course, segmentation for cutting out which parts of that data set you want to use for your training. And there's also a featureization, a set of components to do with featureization. And I didn't go into too much detail here because this will look very different depending on whether you have an NLP application, especially if it's multilingual, if it's not just English, or if it's, let's say, image data or mathematical or time series data. That size can kind of vary dramatically. It could be very complex or very simple, but that's where you're getting all the value. That's where you're trying to take the information out of your training data. And that gets fed into your training components. There's the model building phase that we talked about, where you're actually taking your data in its transformed phase and you're fitting it to some sort of algorithm. So you're basically turning text into numbers and you're using that to get a prediction. There's a validation component. You might want to make sure that the model you're serving up makes sense. You want to have a nice clean audit trail for it. So you want to be versioning it. You want to keep track of which data you've used to build those models. And you also probably want to be training in a distributed way, because that means you can take advantage of all the benefits of using cloud computing and having all of those resources available to you. And hopefully you're also doing continuous training so that anytime new data is coming through, you're updating your models and you're serving up something that's fresh and not stale. And another sort of area of components in these systems is your serving infrastructure. That's your REST server. That's how you're actually giving predictions to people who are looking for them. And the rest of the application, that's your business logic. Those are all of your app-specific components that make up the rest of your system. An interface for users to interact with it. Maybe that's mobile, maybe that's web. It could be anything. And then a load balancer to make sure that more than one person can access it. And then some of the platform-wide configuration, process management, making sure that resources are being utilized effectively in the proper way by the proper components, monitoring, logging, hopefully, and then security. Of course, you want to prevent access to your data by people who shouldn't get it, and then hopefully also some continuous delivery components. All right, so let's move on to a couple of, these are just sort of some lessons learned. These are some common denominators that I've seen among applications that can really make a difference. And these kind of separate the good applications from the bad ones. And the first two that I would mention are just robustness and resiliency, and just making sure that an application can handle any failures, that it can recover from them, that it doesn't go down when one of those little individual components fails. It's important to have redundancy and to make sure that you're always available for your users, because there's nothing more frustrating. You can't, an application isn't, your users are going to go away if your application isn't there whenever they need it. The other thing is that if you're operating in the cloud, you want to be able to scale up and down according to what jobs you're running, and you don't always know that in advance. So auto-scaling is important. Gone are the days when you have to predict exactly how many machines you'll need and exactly when. And you're really losing out on a lot of the benefits of being in the cloud if you're not scaling up and down automatically based on when you're running training or any of the other things. Another important thing is being able to constrain those resources that you're using. So training is really CPU heavy. You need a lot of RAM for it, but you don't want that to interfere with your serving layer. because when you're serving, if you have a slightly stale model, that's okay. It's much better to serve up a stale model than no model at all. And if you have everything running together, you really need to be able to sandbox those resources so that they don't conflict. From the same token, you don't want your logging job to interfere with training and stop you from being able to reproduce, to produce fresh models. Another important thing, I feel like this was pretty obvious in traditional software development, but it hasn't quite made it into machine learning yet. It's still kind of low priority, I would say, but it's definitely gaining traction. And this is important for any type of auditing, especially if you're in one of those industries that requires it. And you don't just want to know which model you use, but what data went into that model and any configuration parameters surrounding that. You want to be able to recreate that. And another thing that sort of came from the app dev model is this concept of continuous delivery. We saw so many benefits from it in that space, and machine learning is no different. There are a lot of reasons why this makes sense. We'll go into this a little bit in more detail. I'll show you an example of what that looks like for an NLP application. And the other thing, this becomes important, the resource constraints becomes important if you have everything in one place. I know a lot of people like to separate things, especially larger companies, because they sort of, economies of scale, they think it's easier to manage, but I have seen a lot better development cycles whenever a full application is in one place, so literally the full stack. And I'm not sure how to describe that other than it's easier to wrap your head around, and it's easier to keep everything in context if it's in one place. It also means that it's easier to sort of forklift between environments. So when you're going from developing on your laptop into a dev environment, into test and production, it's a lot easier if that's all just sort of one thing that you can forklift. And that is also trivial if everything is in source control. If your entire cluster state is living somewhere persistent, that means that you can very easily spin it up somewhere else with different parameters very quickly. If it's in one place, then it's all in source control. Automation, so if you want continuous delivery, not just from a deployment perspective, but also having tests, that is very much standard in the app dev world, and it definitely should be that way in machine learning. So having a framework for that and being able to run those constantly will help you iterate faster. And that also helps you empower your engineers and your data scientists, because if things are automated, if they deploy automatically, then you can sort of front load any approval processes and any sort of human intervention necessary into the front of the process, and then everything just sort of gets deployed. And that's a much shorter development cycle, and it's more empowering. It means that someone can make a change to the system more quickly without a whole lot of overhead. Another thing I've seen kind of change the game, I see startups take advantage of this a lot because they just don't have the resources to be able to roll their own frameworks for everything that they need. And so if you don't need to manage it yourself, there are legitimate reasons to manage your own frameworks, but I think they are less prevalent than a lot of people tend to claim. So if you don't have a really good reason, a lot of engineering hours have gone into hosted solutions, into frameworks that are designed to just give you a service to utilize, and that means that you can focus on the value add for your business and not all of the overhead around it. And it also means that those engineering hours are still being poured into that, so that without you having to do a single thing, that framework keeps getting better and better. So utilize managed services where you can. And that doesn't mean that you have to be locked into any vendors. If you choose open source frameworks and design your code in such a way that you can take it with you, even if you never have to utilize that, even if you never actually change providers, the psychological effect of that can be, don't underestimate that, because it can be significant. Just knowing that your team could walk up and leave anytime can give you a feeling of empowerment and can help you make decisions along the line. So another thing to remember is, I hope you're logging and monitoring. Store everything, even if you don't think you need it. Put it, just tuck it under the mattress for a rainy day. Not just your positive data, not just your positive training data, but also the negative training data. And if you're not sure how to get that, you can always add feedback to your UI. But any additional data that you can collect from your NLP systems can make them better over time. So even if you don't know of a way to use it now, collect it, because it can come in handy later. And another thing is just communicating progress. This, I can't overstate this. This is something that I haven't seen in a lot of places, but where I've seen it, it's actually resulted in better productivity because people are paying attention. They're, like, engineers are thinking about the goals and having a regular pace for reevaluating your progress, looking at metrics, and sort of communicating that to a broader team can be really helpful. And it can also help you see the kind of traction that you've made so far. All right, so now I want to look at a couple of examples. Now I'll just go, this is just going to be a very brief one. If anyone's familiar with Duolingo, I love this company. They have done so many amazing things. But I really just wanted to show, they wrote this really great blog post. It's maybe a few years old now, and it was when they migrated their architecture from Python over to Scala. And I really liked the way they diagrammed this out because, so this session generator piece right here, this is where a lot of their really cool NLP is happening. And this is how their users are interacting. So this is kind of the entry point for the system. But you'll see that everything in red, all of these are hard dependencies. So nothing can come in or out of their API without all of these systems being functional and operational. And that is such a common pattern. I see that everywhere. And I'm sure that if we looked at the real diagram, it would be slightly more complex. I usually see, much more complex diagrams than this. But this is such a common pattern that as systems develop over time, you sort of lose track of where those dependencies are. And they ended up re-architecting their system. And when they changed it, they ended up with a single dependency. That means that they didn't have all that network overhead. They didn't have all of those potential points of failure, and it made a huge difference for them. And the reason I highlight this is not to say that everyone should migrate from Python to Scala. I love Scala, but I also love Python. That's not the point. The point is that when they re-architected, when they redesigned their architecture, their latency changed dramatically from 750 to 14 milliseconds. That means that it doesn't matter how good your NLP is, because if your larger system architecture is not suitable, it might be unusable for your product and your company might never survive. Like, it's all about context, and NLP is important, but it's not the full picture. So take a step back and make sure you understand the broader context. Okay, so I want to move on to, I'd like to talk about Cordoba's architecture. Well, this should look very familiar. This is the sort of canonical web application that we talked about a little bit earlier. And first, just a disclosure, I was employed by Cordoba in 2017 prior to joining Google. So I have a lot of context on this. And so their system, before I get too far, what is Cordoba? It's a startup that has a B2B SaaS internationalization platform. So it's a way of managing strings and using machine learning to do so, to provide a localized version for individual users, both across languages and then also just personalized within languages. So there's a lot of NLP involved in that. And let's see, what else did I want to say about that? Yeah, so they had a really clean architecture, lots of different microservices, very specific to each of the business logic. It was really nice. And they ran this on GCP. This is just a sort of sampling of the types of services that they use. I think pretty central to it is the Kubernetes engine. This is a managed Kubernetes framework, so that all they had to do was define what their objects looked like, and it just sort of ran on its own. They used cloud storage, PubSub, all kinds of different things. This is kind of just a subset. But the cool thing about Cordoba is that they didn't start running on GCP. They actually started on AWS. And they made some really key architectural decisions early on. They chose a lot of these open source technologies, and they went from being sort of roll your own open source binaries on virtual machines. They moved from that into a managed services on GCP environment. And that meant that the application code itself didn't actually change very much. They were able to continue adding new features and changing the application as normal while things sort of developed on the back end a bit differently. But the work in migrating was mainly in just wiring up the automated processes for running that code. And I think that was a really good decision on their part. And it was a really good experience for them. I think it was mostly cost-driven. Like, why would you just up and change cloud providers? As a startup, you're very cost-conscious. And I believe that it made, for what they were running, it made a significant difference to them. And so it was worth moving over to managed services. All right, so there's a lot going on this slide, so bear with me while I explain it. But I really like this diagram. Okay. So I think I mentioned the word GitOps before on another slide, and I promised that I would explain it here. Okay. So this is a diagram of, this is an example of GitOps. This is a diagram of how Cordoba's deployment process worked. This is the continuous delivery process that I promised you I would show you. So let's start over here at the bottom right. This is the live platform. This is everything that's running. This is what's available to the user. This is the product. And this is running on Google's Kubernetes engine. And all of the definitions for those objects live in a Git repository. So that could be GitHub, it could be Google's source repository, it could be Bitbucket, wherever, it doesn't matter, it just needs to be somewhere. And there's this really cool agent over here. Has anyone heard of the company called Weaveworks? They're kind of a small startup. I see a few hands. So this is the Weave Flux agent, and this is open source. You can download this and run it on your own cluster, but Cordoba chose to use their hosted cloud solution. It's just called Weave Cloud, and they have this really neat agent that you connect to your cluster. Okay, so what's important here, I'd like you to look at this line. This is a very strict dividing line between the ephemeral layer and the persistent layer. So everything up here defines what's down here. This is the active sort of running instances, and they all get their instructions from up here. So this Flux agent, this Weave agent, is keeping an eye on three things. It's looking at what's running inside the cluster, and what's supposed to be running in the cluster, which is what's sitting in source control. And then it's also watching the container registry for new versions of things that it thinks maybe should be running on the cluster if they're not already. So this little agent right here keeps track of what's running, what should be running, and what it thinks should be running. And when it notices something happening over here that it doesn't recognize, that isn't up here, it gets rid of it. And it overwrites it with what's in source control, which means that any change you want to make to your cluster, you make it up here. So you commit a change to your Git repository, and that change gets picked up and automatically deployed, which is really cool when something goes wrong because you have a whole history of all the things you tried when you were trying to fix it. You can see what worked, what didn't. And if anything changed, you know exactly what changed and when across your entire system. Remember how we talked about putting everything in one place? This is why. So, and the other good thing for auditing purposes, a lot of industries have really strict requirements on if there's something running, you need to essentially guarantee that nothing is running on your cluster that shouldn't be there. That's what this agent does. Okay. So it's watching this container registry. That could be Google's container registry, Docker Hub, wherever, it could be anywhere. How do things get into there? How do images just arrive there? Well, that's where the container builder comes in. It could be a roll your own Jenkins instance on a compute node. It could be Travis, Circle CI, whatever. Cordoba happened to use Jenkins. And this instance is watching your application code. So this is your application repository, and it's watching for new code changes. So when someone merges a PR, there's a new commit hash, and Jenkins picks that up and sees, oh, I need to build a new image. So it picks it up, goes through the build process, pushes it out to the container registry. Your Flux agent notices that there's a new version available, and it will make a commit to the GitHub repo and then also deploy it onto your cluster. And this is amazing because all you've done is you've merged a PR. So as a data scientist, to know that you can get stuff out into your cluster after like, okay, so maybe you needed a PR approval, maybe you needed a review, but all of that is front-loaded. And once that's done, you can literally watch it go out into your cluster. And that's the cool thing. That's the essence of GitOps, is there are three main benefits to that. And the first is really just it optimizes for those person hours. Because that development process then becomes, I'm creating a new feature that may take me a while, but I push out that branch and I create a PR, and then I kind of go away for a while. I let someone review it, I let someone look at it, and in the meantime, I move on. I'm creating a new feature branch, I'm working on something else, and these things are happening kind of in the background. It gets approved, the agent picks it up, it gets deployed, and then I might notice, okay, let me go in and verify it. Let me go into that environment and make sure that what I developed operates well with the rest of the application. And in the meantime, someone else is reviewing the other feature branch that I created, and I can move on to a new one. And so it's this really nice rhythm of development that, like, it's kind of hard to describe. So it's not just about you're not having to physically deploy your application components, but it's about this rhythm and the way you can sort of develop in this process that's a lot more efficient with the whole GitOps infrastructure in place. The other thing is that it empowers your engineers and data scientists. Like I said, it sort of front loads all of those human-generated approval processes. And once those are there, it just sort of happens. And that's a very empowering thing, especially in companies where roles are very specific and there's a lot of handover between teams. But the other major advantage is just that because you have that persistent layer, you know exactly what your cluster state was when, and so that is always recoverable, and you have that historical record. That means it's easy to replicate those environments. It's easy to forklift them. If something goes down, you can literally stand up the exact same instance in a sort of trivial, scriptable way. All right, so this brings me to sort of the next era. Now that all kind of seemed like really cutting edge. This was 2017 that all of this was being built, and maybe December of 2017 there was this new project that was announced called CoopFlow, and it was formed with the vision of providing like a standard deployment infrastructure for machine learning applications like Cordoba's, but without all of the custom setup. So taking that idea and making it more generalizable so that anyone can use it without having to be very specific to that one startup. So who's it for? For data scientists, engineers, project managers, really anyone. It's designed to be easy enough and composable enough that you don't have to have an advanced degree in order to build a machine learning application. And it's meant to be portable. So one requirement is that, in fact, the only requirement is that you have a Kubernetes cluster. So as long as there's Kubernetes running, you can run this ML application. And if anyone was in Copenhagen last week at KubeCon, they just announced the 0.1 release. And so it's still really fairly new. I think end of 2017 is when it was started. So it's still pretty young, pretty early days. But this is to take away a lot of the pain of building that platform because we really don't want to have to be experts in all of those different components because there are a lot of them. It's not just machine learning. There are kind of three important concepts within CoopFlow. Scalability is really important, and that's why Kubernetes was chosen as a platform of choice, because so many of the scalability issues are solved sort of by solved for free just by using Kubernetes. They're just native to that platform. And it also reduces the variability between those services. So remember, if you have everything all in one place and you have good sandboxing between, if you have a good way of defining how many resources each job is allowed to consume, then you can standardize across your platform, and that machine learning component doesn't look any different from your serving component or your logging and monitoring. And that's a lot less headache to maintain. And when you're developing those applications, the other reason why it's important to have everything all in one place is that you want to be able to test that in lots of different environments. I want to be able to test it right here on my laptop. I also want to be able to take it into any number of cloud providers or on-prem or like hybrid environments, and you don't want to have to change any code. So just a little bit of config, you should be able to do that. So portability is important. And then the idea of composability. This is where we have kind of Lego bricks for developing the machine learning components, and that we don't have to know all the advanced math, and we don't have to get into the sort of deep details of that we're kind of used to in developing ML applications. So another goal is just to support the full product lifecycle from the very beginning. Like when you're building something from scratch and you're doing a lot of experimentation and you're still trying to figure out what it is that you want to build, CoopFlow wants to support you from scratch all the way up into production deployment without you having to sort of migrate onto different platforms. And we also want to be able to take advantage of specialized hardware like GPUs, TPUs, anything else that might come out tomorrow, because you can reduce your costs and really improve your model performance. Okay, so what is it? It's Kubernetes. Wherever Kubernetes runs, you can run it. And it does this by utilizing custom resource definitions for distributed training. And it sort of natively adopts these Kubernetes patterns, like splitting things out into microservices and managing things declaratively, like we saw with our Docker file and Jenkins file earlier. And it utilizes CaseOnit. CaseOnit is a third-party tool. It's also open source. But this is something that it uses in order to ensure that you can take your application and move it between different environments, different clouds, laptop, whatever. And then it also supports multiple frameworks. So not just TensorFlow, but really anything, Scikit, XGBoost. There's a lot of movement in the community to support more and more, and so kind of the sky's the limit with that. But the idea is not to constrain it to any specific framework and to make it something that's broadly applicable. So I want to take you through an example. What does this look like and how would you use it? There's a good blog post written by a GitHub engineer named Hamel Hussein, and he looked at how to summarize GitHub issues by looking at the text within the issue body. So he used TensorFlow and Keras to do this, and he has a really neat tutorial. There's a really cool notebook where you can sort of walk through all the steps yourself. And we took that blog post and we turned it into an end-to-end CoopFlow example where you can see where there's a markdown that takes you through each of the steps of installing CoopFlow on a cluster, using CaseOnit, setting up a persistent disk so that anyone attached to that cluster can access the same data. And Jupyter Hub is kind of the first entry point, because this is where his blog post really comes in handy, because he has a really nice notebook. And Jupyter Hub is important for that exploration and experimentation phase. So when you're building something from scratch, you can choose your data set, do your slicing and dicing, try out lots of different kinds of featureization. There are lots of different options. Train any number of models, compare them, and do a lot of plotting along the way. And Jupyter Hub is really good for that. It's kind of the industry standard, and there's a lot of things built into it, like security, reproducibility, a lot of things that CoopFlow didn't have to build itself. It just sort of supported the use of Jupyter Hub on the platform. So this is what it looks like if you train a model using this notebook. And let's see. Okay, so besides notebooks, after you've gone through that exploration phase and you are ready to, you know which model you want to use, then it's time to start serving it. And there are a couple of ways to do that within CoopFlow. There's something called a TF job where you can deploy, you can perform training of TensorFlow models, supports tensor to tensor, and then once you've built that model, you want to be able to serve it. There's something supported called Seldon IO, which helps you wrap it in a REST server, and it even gives you sort of a really simple web app, a UI, with which you can interact with these services. And this end-to-end example kind of takes you through each one of those steps and gives you a guide for how to do those. And this is what it looks like in the end. This is the super simple web UI where you can put in the text of an issue or populate any random one or any GitHub issue URL, and it'll generate a title for you. So you can try it yourself. This is the link to it. It's all on GitHub. It's github.com/CoopFlow. CoopFlow is the organization, and it's in the examples repo. And it's the GitHub issue summarization example. And that lets you run it on your environment, wherever you want. But there's a really cool service called CADA where you can do everything in the browser. They kind of host things for you, and they have a really good step-by-step walkthrough of this particular example. And then also this site right here, oh no, I went back too much. So this site, give me a second, this one that we saw right here, that's actually live, and you can interact with that if you go to this link right here. It's githubdemo.coopflow.org. And none of that would be possible without these pretty cool guys. Jeremy is the lead engineer for the CoopFlow project. He keeps things on track and makes sure that features get implemented. And Ankush is an engineer on his team. He put together a lot of that example. But this is really kind of just the beginning for the project. We're still at the beginning of that era where we're building these modular components, and there's still a lot of work to do. The setup could be easier. There are a lot of Kubernetes features that we want to take advantage of, and there are a lot of ML libraries out there that aren't supported, that native support would make a lot of sense for. So these are a lot of the companies that have been involved so far. It's not just Google, it's an open project. Community meetings, we have people from all over the world, and we sort of alternate time zones. That way everyone can attend. But the Slack team is a good place to start, or go on GitHub, pick up some issues. Feel free to, as you're going through that example, to file some bugs and let us know how the experience was. That's always welcome. So we're nearing the end of the talk, and I just want to really quickly go over what I think the future looks like. And I think we're very close to, we're in the process of building that sort of higher level language for machine learning, that sort of C++ of ML. And I think we'll get to a point where composability is so good that it just becomes sort of trivial to build a classifier. And we'll be able to just ask our Google Homes to build us one. But what I wanted to leave you with is just sort of encouragement to keep building, keep contributing, and let's get to that next phase, of machine learning. So that's all I have. I believe we have some time for questions, if anyone has anything they would like to ask.
Alô? Perguntas, se alguém quiser fazer em português, eu posso traduzir. No questions? No? Okay. So, thanks a lot. And nós voltamos depois do intervalo para a última palestra da tarde, que vai ser